They don't tell you about the smell until you have to live with it. You get used to certain smells aboard a warship: the cold bronze tang of salt on steel, the sweet graphite dust from the bearings, the diesel breath of the auxiliary gens. But when a missile tube starts to give off heat, it is not the smell that gets you first. It's the way the bulkhead seems to pull attention, like a hand tucking in a bedsheet. I was an engineer. My world was valves and seals, pressure charts and bolt torque specs. I'd run S5W era plants and modern reactors. I'd learned the difference between a pump that groaned and a pump that talked back, and I could find a leak by feel if I had to. On that patrol, we were an SSBN on deterrent patrol, quiet as a coffin and precise as a watch. Our missile compartment was a cathedral of steel and bureaucracy. Each tube a sanctum, each canister a locked book of rules. The missile tubes are not just missile holders. They are plumbing, venting, piping, interlocks, safety, and occasionally violent chemistry. The boat's schedule makes them routine. The work keeps you sane. A glowing tube does two things. It violates a procedure and it steals attention. We ran daily checks: seal integrity, vent valve positions, canister interlocks, the methane scrubbers on the deck, the tube overboard drains. There's redundancy everywhere because a tube that fails does more than fail its hardware. It threatens the whole ship. SLBMs, like the Trident, are cold-launched from their canisters by gas pressure. The motor ignites only after the missile clears the water, which is by design a safety feature. But that design doesn't immunize the system from chemistry, stray heat, or human error. You can have a benign cold launch system and still have a bad day if a seal fails, seawater mixes with residual propellant compounds, or a pyrotechnic charge cooks off. Cold launch doesn't mean no heat. The physics still breathes. The first sign was a thermal blip on the tube wall sensor right after the midnight watch change. Not a full alarm, the sensor spiked and then settled, but the log printed the blip in a way that catches a pro's eye. We have maps for everything: pressure, humidity, bolt torque specs, even thermal baselines across the missile house. Engineers memorize those lines like sailors memorize constellations. The blip was a local, narrow hump in the heat map. Tube 3, starboard quad, section near the intercept plate. I walked down with the handheld infrared scanner because even in a boat of instruments, your first sense is skin. The IR probe painted the lip of the tube in crimson, where the rest of the compartment read in steel gray. An engineer's instrument is a truth-telling toy. The screen lit a single lie. I called for an immediate local inspection and sealed normal ops on that tube. Rule 1, you don't open a tube you suspect of thermal excursion until you've traced the heat path. Rule 2, you do not panic. We moved through the checklist: check external hull temps, check interstitial venting, cycle the tube's purge sequence, verify the canister doors were in their closed and locked state, poll the tube overpressure alarms. We also ran a thermal sweep on the adjacent fluid plenums and the nearby hydraulic accumulators. All looked nominal, except the tube wall and the immediate canister skirt. Rules are scissors. They cut panic into smaller, manageable bits. We hooked a portable thermocouple and placed a contact on the canister skirt. It read 85 degrees centigrade and climbing. That's hot. Missile canisters are meant to sit near ambient. Electronics can tolerate temperature excursions, but the propellant, seals, and pyrotechnic elements in or near a tube are sensitive to heat. An unexpectedly hot canister can degrade O-rings, bake adhesives, or in worst cases, cook pyrotechnic initiators. Cook in that sentence is not metaphor. For a missile system, it means turning stable components into volatile ones. In fact, accidental silo and missile fires and heating events have a long, ugly history. Titan II and other silo accidents show how a small leak or a spark can escalate into catastrophe if not contained. 90-degree errors are boring until they turn into combustion. The questions began circling like gulls. Thermal conduction from an electrical fault? A stuck heater? Hydraulic friction? Or something chemical inside the canister? We used cameras through the inspection coupling and saw nothing remarkable. The missile skin showed expected placards, the canister liner looked intact, and the hold-down clamps were in place. We cycled the purge gas. We blow inert gas through the tubes during maintenance windows to prevent corrosive chemistry, and sampled the exhaust. The gas came back with a faint nitric tang on the handheld chem sensor, a note that made the pit tighten in my stomach. Nitric acid smells like pennies and rust. You don't want nitric chemistry anywhere near missile structures because it is corrosive and because certain oxidizers form from it when hypergolic compounds are present. There are historic precedents for seawater mixing with missile propellants to create acid and subsequent fires or explosions. Look at K219 and other SLBM accidents, where seawater ingress and seal failures created violent consequences. The national interest. A smell on the exhaust is a radio from chemistry. You answer it by being very careful.
We dialed telemetry into the damage assessment channel and put the tube on heat watch, automatic logging at half-second intervals, multiple thermocouples and an independent IR camera on a boom so we could watch the canister skirt without opening anything. On the console, the numbers read like a hand getting warmer and warmer, 85 degrees centigrade to 92 degrees centigrade to 107 degrees centigrade. The canister skirt was glazing, the paint began to thermally break, and you could see the sheen change. The operational order was strict. Start containment, notify the reactor and weapons control chain, and prepare environmental isolation. The XO ordered the compartment evacuated to keep people safe. We drew fire blankets and set up cool mist deluge on standby. There is a ritual to this. It lowers the long odds of catastrophe, but it does not remove them. Containment is a ballet in steel. We tried to reason the heat away. Friction in a bolt, hot air trapped in a siphon, electrical arc in a nearby junction. We wet-checked every circuit and every pump. Nothing. No arc signatures, no current spikes. The uplink to the tender's weapons engineers was terse. Thermal anomaly in tube 3. Possible oxidizer reaction. Recommend analysis. The weapons team's reply pulled in 2 words that are efficient at killing theater: stand by and recovery plan. Those are lines that mean experts will talk while you hold your breath. Stand by is a professional hush. The IR camera finally showed the detail, a small ring of active heat near the rear of the canister where the maintenance hatch sits. It was not uniform. Instead, it pulsed, small thermal flickers that suggested an active process, not a passive, decaying heat. If it had been a simple hotspot from a frayed heater cable, a profile would have smoothed quickly. These pulses were rhythmic. We ran a spectral analysis on the temperature time series, and the curve had peaks at regular intervals. That pattern had a signature: periodic energy releases at low frequency. In engineering terms, that can mean mechanical rubbing at a rhythm, slow exothermic reaction steps, or small controlled burns, not good in a sealed weapons bay. Instruments do not hiss to themselves, they tell you a story. The weapons tech back on the tender suggested one more step before we commit to any invasive action. Take a small controlled purge sample, route it through a chromatograph on the tender's portable lab, and check for unusual oxidizers or propellant decomposition byproducts. They warned, if we see nitrogen oxides and nitrates combined with traces of hydrazine-like species, that's a chemistry no man should stand next to. We prepped the sample valve and bled a measured puff of the tube atmosphere through the sample train. The chromatograph read with the economy of bad news, strong NOx peaks with a faint trace that matched the profile of unsymmetrical dimethylhydrazine UDMH decomposition markers and nitrated organics. Hypergolic fuel traces in a missile tube aboard an SSBN? That makes the hair on your arms stand up. A lab printout is a confession in ink. If you are reading this and thinking, how would hypergolic fuel get there? So did we. Modern SLBMs use solid propellants. Trident D5 is solid fuel, not UDMH, so direct hypergolic leaks are unlikely with that family. But the ambiguity is the worst bit. There are service chemicals, maintenance residues, older missiles with different compounds, corrosion byproducts, and 1,000 tiny places where seawater can meet metal and make ugly chemistry. And there's always the horrifying edge case, a foreign object like a lost piece of maintenance gear lodged in a vent line, an old seal degraded to the point where trapped water and an oxidizer reacted on a heated surface, or, God forbid, overpressure causing a pyrotechnic primer or squib to begin to outgas. We had to assume worst until proven otherwise. Improbable is just a small list of unchecked items away. We prepared the hardest decision, to cold vent and isolate the tube, a procedure that would vent to the exterior and risk plume signatures and acoustic noise, and it could complicate strategic posture. But a glowing canister can burn people and cook off pyro. The captain and the weapons officer weighed it fast. Their faces were small and expert, and told me to prepare the cool mist deluge and to set up an emergency exhaust to plume in a controlled vector if needed. We would not vent unless the chemistry accelerated. Strategic posture meets fire control in a single command. That night, the pulses accelerated. The thermal flickers grew in amplitude and started to bleed to adjacent supports. The IR camera showed a localized convective cell forming above the canister, hot gas rising and then curling along the missile house ceiling. The alarms whispered like a throat clearing. We prepped personnel for donning breathing gear and moved non-essential crew away. On the console, the chromatograph printed another run, NOx up, nitro organics up, and an unidentified peak that none of our onboard libraries matched. We clipped the chromatograph output and encrypted it into the mission log. Then, for the first time in my life on a boat, I felt something that was not professional curiosity or even fear. I felt a cold, certain expectation that a mechanical system we had long trusted was trying to tell us of a danger we could not yet name. Logs are legal. They are also little prayers. I will stop here. The part where we act, where the deluge is triggered, or the tube vents is for Section 2. That part has to be told carefully. The escalation, the attempt to cool, the way the chemistry answers, the human choices, and the institutional aftershocks. If you want Section 2 now, I'll continue straight into the cooling, the attempted intervention, what we discover in the canister, and how the Navy handles the aftermath. All in the same voice, with deeper technical detail and citations for the key facts.
The deluge started like a breath, a slow pressure in the pipes, a metallic sigh, and our IR readout went red in a line that felt like a pulse racing toward a door. We pulled the cool mist deluge into place in the way a mechanic prepares for a cut. Calm, precise, checkboxed. The nozzle array sat over tube 3 like a coronet. The pumps were primed. The crew wore breathing gear on the benches. We had minutes, maybe less, depending on the chemistry inside the canister. The captain ordered us to try localized cooling first. The plan was to snuff whatever was cooking without venting the tube to the ocean, because venting would be both a tactical and environmental problem. A decision to cool rather than vent trades one danger, internal cook-off, for another, unknown chemistry trapped inside. We started the deluge in soft pulses.
Water spray can cool surfaces effectively while limiting thermal shock to sensitive electronics and ceramics. But water is also a wild card around oxidizers. For propellant chemistry, water can be a neutralizer or a trigger. It dissolves salts, moves heat, and sometimes opens pathways for exothermic reactions. The localized IR camera showed the tube edge blanch as cold mist hit it, 107 to 86 to 71 degrees Celsius. We breathed easier. Then the tube wall mapped a tiny re-spike, a flare of heat that erupted after several minutes of cooling and then receded. Those after spikes are the ones that make experienced techs sober. They can indicate a staged reaction. Heat makes a reaction continue in a new regime rather than kill it. When cooling makes a thing flare, you know the chemistry is arguing back. We sampled the deluge runoff and sent the fluid through the portable chromatograph on the tender's lab via a sealed, shielded line. The same setup we used before, but now with the addition of mass spec confirmation. The lab printed the new run in the wardroom, while the boat smelled faintly of ozone. The chromatograph showed an alarming profile. NOx peaks and nitrated organics elevated, and under them a small but clear peak that matched markers for hydrazine decomposition products. Hypergolic propellants like UDMH and oxidizers like nitrogen tetroxide are infamous in rocketry for reacting violently when they meet. The Titan II disaster is a well-known precedent where a dropped tool punctured a fuel tank and led to a catastrophic oxidizer-fuel interaction. That accident is a stark historical lesson in how a tiny mechanical event can cascade. We could not assume our scenario was the same, but the presence of nitrated species plus hydrazine markers was a siren you cannot ignore. A historic accident is not a prophecy, but you do check the boxes it taught you. The LAAD ordnance handling literature and field manuals lay out the brutal math, evacuation distances, hang fire windows, and the protocols for guarding a misfire. Those guides say, if in doubt, remove people and keep observation. We followed that book to the letter.
The manuals are the closest thing to prayer you get in this business. At 0312, the instruments went sideways. The IR readout spiked along a narrow seam, and then, impossibly, the tube's internal pressure sensor caught a transient positive blip, a step change that suggested gas production inside the canister. The chromatograph showed a new, unknown peak that the onboard library did not match. We labeled it Unknown A and ringed it, the way you circle a weird animal on a map. Unknown A correlated with the flare and with a noise we all heard, a deep pop like a pressure plate resetting, followed by a gentle metallic ping. The ping felt wrong because it sounded like something structural adjusting under heat, not the brittle pop of resin. Unknown peaks are the most dangerous sort. They mean you have a thing you cannot name. We were out of comfortable choices. The commander authorized a controlled cold vent. The plan was to route the tube atmosphere through a sealed scrubber train and release in a direction and altitude designed to minimize detection and avoid nearby shipping. Venting was ugly. It could stain the ocean with effluent and change acoustic signature. It could also save lives. We executed. Valves opened slowly, scrubbers engaged, and an exhaust line led the gas away in a vector chosen to minimize plume rise. The instruments charred off a handful of signals, and then the scrubber logged a spike in load, and, in sequence, the canister's IR showed a collapsing hotspot. For 30 seconds, we watched the fire readout drop like someone throttling a candle. You vent to survive. Sometimes survival smells worse than the alternative. Then the worst sound came, an internal alarm, not a mechanical bang, but a series of rapid clicks, a sequenced mechanical signature,
followed by a small, concentrated flame inside the canister, visible in a camera shot through an inspection port. It wasn't a full-scale rocket ignition, but a confined, energetic event. The flame was brief, contained by the canister liner for now, but enough to melt a pair of fasteners and to blow a small patch of scorched liner off into the scrubber stream. Our emergency plan pivoted instantly. Stop venting, close valves, and switch to a passive cool and hold. The priority now was to prevent further energetic reactions and to keep the canister intact until specialist salvage technicians could arrive. Containment is a gamble, where every response changes the odds. While we held, I got the lead diver from the tender to run a remote camera down a maintenance bay and inspect the back of the canister, where plenum and interstage plumbing live. What we saw mattered. There was a small object lodged near a purge channel, a fragment of what looked like a maintenance-grade gasket or tooling material, sunken into a flange groove. Whoever had packed the boat last either missed it or it moved in somehow. The fragment's surface chemistry, after a quick XRF scan, showed high chlorine residues and nitrated deposits. That smell of chlorine in a compressor bay is not pleasant. Chlorine salts plus NOx makes nasty oxidizing salts that can eat rubber and steel. The fragment looked like an old seal, but in the wrong place. The conclusion started bending into the same crooked shape. A foreign object or failed seal had created a small reaction site. Heat and trapped gases had begun a chemistry that produced NOx and reactive intermediates. The tiniest thing, a gasket fragment, can be the match in a tinderbox of chemistry. We were out of comfortable choices. The commander authorized a managed, monitored lift to a secure dry dock, where the canister could be opened by specialists with remote tooling. That option meant mission abort and strategic recalibration. It meant the mission would be cut and the boat routed back under escort. The captain's face tightened. Missions are commitments, but you do not gamble lives over a mission. He ordered return to port. We rode home under a hush of compartmentalized communications and guarded watch reliefs.
Returning to port is the dull sound of a mission ending in humility. The aftermath was a flattened bureaucracy in motion. An incident report went to the Fleet Command and to the Weapons Center. A classified tag went on the sample, on the chromatograph prints, on the remote camera footage. We filled forms and gave statements. The public face of the event, if there was to be one, was the minimal line, "Thermal anomaly in missile tube managed. No loss of life. Boat returned for inspection." Behind that line sat lab reports showing NOx peaks, nitrated organics, traces of hydrazine decomposition, an XRF report of chloride contamination, and a small foreign fragment archived in secure evidence. Official lines tidy the language. They never tidy memory. There were personnel consequences. Someone in the maintenance shop who'd done a last-minute seal replacement a month before was administratively relieved pending investigation. The replacement procedures were audited. Tool control logs were examined and found wanting. A missing torque wrench accountability entry, a small gap in sign-offs, and a note that a vendor crew had been on board for material replacement. In the small world of maintenance, a missing signature is a sunken chew mark in the logbook. It reveals a place where human error can creep in. The official line became procedural lapse with contamination, a phrase that covers neglect without naming catastrophe. It's the language that saves careers, but sometimes does not give you the full technical truth. Paperwork can be a bandage or a curtain.
Months later, the laboratory's in-depth analysis was moved into a secure project archive. The fragment was analyzed in a controlled facility and its residues mapped. The lab's redacted conclusion, the parts they would let the boat read, said, "Contamination consistent with maintenance debris and oxidizer interaction. Recommend stricter tool control, improved seal inspection, and revised purge protocol." That's a good list of mitigations. It costs money, it costs time, it costs embarrassment, and it usually prevents the worst. It does not always satisfy the men who sat in the compartment with their masks on and watched a canister glow. Root cause is a word that both heals and leaves scars. I kept copies of my own logs. I archived temperature time series, the chromatograph PDF, and a frame-by-frame of the IR pulse. I encrypted them and mailed them to a trusted engineer on shore as redundancy. People like us keep a private ledger because public levers can be clumsy and slow. If the investigation's public face changed or simplified, at least the data would remain. We fixed the immediate hazard, but the memory of a glowing tube stays. It makes engineers less trusting of small things and more vigilant where others are casual. It changes the way you torque a bolt forever.